Hi, I'm Martin Phillips from Zumasys, and today we're going to look at the key features of QM Release 4.0. There are two main features here we're going to talk about, one called application profiling and one called data integrity constraints. Data integrity constraints are a means of making sure the data we store in our database is consistent. Common comments about the multi-value models from people coming to it from a relational background is that we don't enforce data types within the file system. As an example of that, an application could accidentally store the customer's name in a field that should hold his customer number. And some of these can be very difficult to track down. Multi-value products tend to validate data as a user types it into his screen or as it is read from other sources, and then assume that it remains valid. Relational products, on the other hand, tend to impose data types that are rigorously enforced when writing to the database. The data constraints development within QM allows a developer to apply rules to any or all fields, and it's done in a manner that cannot be circumvented. What do we do here? How does it work? The constraint rules themselves are stored in field 12 of an A-type, D-type or S-type dictionary item, and in the case of A and S types, they must not involve a correlative. So it is a reference to a real piece of data stored in the file. If there's more than one dictionary item present for the same field, as is very common in applications, only one of them may have a constraint definition included on it, and it will be shared amongst all uses of that field. The constraint rules themselves are expressed in a form very similar to an I-type expression, but we have some additional operations for some common validation requirements and one or two minor restrictions as well. So the constraint definitions are in the dictionary in field 12 of the data defining items. These are then compiled using a command called compile constraints, and that combines the whole set of constraint rules into a single validation expression that is then stored in the data file, not in the dictionary. By storing it in the data file rather than the dictionary, it is impossible to circumvent this, as the write mechanism always just takes the constraints within that file. Expressions themselves, as we say, very similar to an I-type expression, returning true or false, and they must be self-contained. They mustn't make reference to any external subroutines, transfunctions, T-conversions, etc. This is not about doing inter-file data integrity. This is about checking that the data we write in any field has the correct type. There are some additional special data names we can use in the expression. @data is the data for the field you are currently validating. @fno is the field number of that field. @id and @record sound very similar to their use in an I-type, but as it says here, they're not actually the same variables, but they are the record ID and the entire record data. Compound expressions are allowed if we need to do something more complex than a simple expression enables us to set up. And just as with I-types, the intermediate results are stored in pseudo variables called @1, @2, etc. And they can be used in exactly the same way as in I-types. There are 5 additional functions added for common validations. Very often we want to check that a field contains an integer value, and we might want to check it's an integer value in a particular range. The integer function allows us to do that, and we can specify low and high range checks, both of which are optional. Similarly, the number function says numeric value, so this time it might not be an integer, but it must still be numeric. The string function is checking whether the data is a character string within a particular length range. The matching function checks against pattern matching and can take multiple patterns, just like the matches function of BASIC. And the exists is a file integrity check, and it's the only interfile check we have of any sort in here, just checking that the field in my current file exists as a record in some other file. So what happens at runtime? A write operation on a file with data integrity constraints defined executes the constraint expression in a manner very similar to a pre-write trigger. If the file uses triggers as well, they're executed before constraint verification. And unlike a pre-write trigger, a constraint rule can't alter the data that's being written. It simply checks it complies with whatever rule we've determined. If the validation fails, the default action is for the write to be abandoned, and it will take the on error or else clause of the write, depending how it's written in our programs, or it might throw an exception, in this case sys.file, sys.constraints. And we can find the field number of the field that failed in this validation in the @fno system variable. The compile constraints command also has options to apply a couple of mutually exclusive alternative ways to handle verification. With the logging option, verification takes place exactly as before, but rather than failing the write, it simply logs a message in the erlog file. The disable option, on the other hand, completely disables checking, so the checks can be defined in the dictionary but temporarily disabled for one reason or another. We can do on-demand constraint verification when we need to with a verify constraints command. And this goes through the file looking at all the records that are already stored there, checking whether they comply with the constraints. And it's useful if you've used either the logging or disabled modes, and it's useful if the constraint rules have been changed in a file that already has data in it. We can check that the data that's already there complies. And for programming purposes, the QMBasic validate function can be used to verify compliance without attempting to write. So simply saying, if I were to write this data, would it be acceptable? This has been Martin Phillips from Zumasys.